Welcome to Complex Analysis Lesson 19. We're going to cover Taylor series, a special case of the Taylor series, the Maclaurin series, and something called the Laurent series. These are all for complex variables. I know for Taylor and Maclaurin, you've probably seen those before for real variables in calculus, but we're going to do the complex version of those, and we have quite a few examples also. The Taylor series for a complex, or for that matter, a real valued function, is an infinite sum that is expressed in terms of the function's derivatives at a single point. And we already saw this for a polynomial several lessons back. We did a Taylor series for a polynomial. And this is more general. It'll be for any function that's analytic in a disk, centered at z sub 0 and radius r. The less than means the boundary of the disk is not included. And the Taylor series at this point, z sub 0, is given by this series here, a sub n times z minus z sub 0 to the nth power in this disk, and then the coefficients here are determined by taking derivatives. So you see, if you have a polynomial of degree n, by the time you get to the n plus 1 derivative, the derivative is 0, and all following derivatives are 0. But for other functions, we'll see that you actually get an infinite series, and we'll get to some examples in a minute. Yeah, and the convergence is uniform, as we discussed in the previous lesson. This convergence is uniform in the disk, less than or equal to r, where r is small r, where r is less than capital R. And the series representation is unique. So this is a bit of a complicated proof. If you're interested, you can check the book by Brown and Churchill, which I've referenced here, and actually they proved the theorem in section 58, and I believe in section 66 they addressed the uniqueness part of it. And when z sub 0 equals 0, it's traditional to call the series a Maclaurin series. So that's basically a special case of the Taylor series. So let's take an example. F of z equals e to the z, which is analytic over the entire complex plane. So our disk is actually the entire plane. We don't have any restrictions there. And we know that the derivative of e to the z is e to the z. So it's pretty easy to get the coefficients here. The nth derivative is e to the z. Evaluate that at 0. And you get e to the 0 over n factorial, so it's just 1 over n factorial, and you plug that into the formula, and you have z minus 0 to the n divided by n factorial. And since we're centering the series about the point z sub 0, that we call it a Maclaurin series. Okay, we have a few basic operations we can perform on series, and it's pretty much what we've seen in calculus. So if you're given a Taylor series, f of z equals this here, where you have your coefficients a sub j, and then another Taylor series where the coefficients are b sub j. Both of them are centered about z sub 0, and they're open in the same, I should say they're analytic in the same open disk about z sub 0. So under those conditions, you can multiply by a constant, and you'll get a Taylor series for c times f of z. It's just a matter of multiplying the constant c inside of the summation. And then you can add or subtract them. So the Taylor series for f of z plus g of z is you just sum the coefficients, and if you want f of z minus g of z, then you would subtract the coefficients. And the proof follows from the fact that a linear combination of two analytic functions is analytic. We saw that when we talked about analytic functions, that you can add them, subtract them, you can even divide and multiply them, but we're just using the additive and subtract properties here. So on this slide, we're going to do the Taylor series, or actually the Maclaurin series, for the sine of z. And recall from before, the sine of z is e to the iz minus e to the minus iz divided by 2I. I broke it up into two pieces here so that we can use the Maclaurin series that we derived in the previous slide twice, once here and once here. And then also using the theorem that we had about the adding and subtracting Maclaurin or Taylor series. So we have here sine of z is 1 over 2I. We just factor that out. And then we plug iz into the Maclaurin series for e to the z and do the same for e to the minus iz. And then we subtract these coefficients and get just one summation here. And notice we took the minus 1 to the n and we brought that out here. So we have a 1 from this term and a minus 1 to the n from here. And then once you factor that out, then you have I to the n, z to the n over n factorial from both of these. So we can do a little bit more reduction. This part of the coefficient, I should say, when n is even, this is 0, right? Because you get minus 1 to an even number is 1, so you get 0. So we only have odd terms. So we can just evaluate this at the odd values, 2n plus 1. And that's what I did here. I plugged in 2n plus 1 for n in 4 places here. And then we get this expression. And then there's some reduction possible. First of all, when you put in, this is an odd number here, 2 to the n plus 1 is an odd number. So this gives you a minus 1, and you have 1 minus a minus 1, so that's 2. So this becomes 2. And then we have some additional work we can do here on the, I just said this here, but you have the I to the 2n plus 1 equals I squared to the nth power times I to the first. And of course I squared is minus 1, so you get minus 1 to the n I, which is what I plugged in here. And then the other terms I just left the way they are. So this sine of z has this Maclaurin series about z equals 0, and the domain of applicability here is the entire plane, the entire complex plane. As our second example, we'll take the log z and find its Taylor series in this case about the point z equals 1 and within a disk of radius 1. So the first thing is we take the derivatives of the log. We already derived it, the log, derivative of the log to be 1 over z, and the second derivative is minus 1 over z squared. Then you get a plus 2 factorial z cubed, and so on, and you get, for the nth derivative, minus 1 to the n plus 1 times n minus 1 factorial divided by z to the n. Then we apply our theorem for finding a Taylor series. And since we're evaluating the series centered at 1, we plug in 1 into this formula, and you get z to the 1 to the n, is 1. And you get the n minus 1 factorial, but you're divided by n factorial, so you just get an n in the denominator, and then you have this minus 1 to the n plus 1 term. And so we plug that into the formula, and that's what we get. This is the Taylor series for log z at point z equals 1 within this disk here, z minus 1 less than 1. On this slide, we have a theorem concerning the derivative of a Taylor or Maclaurin series. If a function f is analytic at a point z sub 0, one can determine the Taylor series of the derivative of f by taking the derivative of the Taylor series of f of z on a term-by-term basis, and the resulting series converges on the same open disk as the Taylor series of f of z. So for proof, we can find the Taylor series of the derivative two different ways. First, we use theorem 137. That's our Taylor series theorem, and we get this expression here. Notice that the first thing here is the derivative of f of z because we're doing the Taylor series for derivative of f. Now, if we do it by taking a term-by-term derivative of the Taylor series for f, we get the same result. So that pretty much proves our theorem. The other point is that from theorem 131, the Cauchy's integral theorem, we know that the derivative of f is analytic everywhere f is. So these two series, taken in two different ways, have the same region of convergence. We'll show an example of this in the next slide. So we can use our theorem from the previous slide to find the Taylor series for the cosine based on the fact that we know that the derivative of the sine is the cosine, so we can find the Taylor series for cosine about 0 in this case by taking the derivative of our formula for the sine of z. So we bring the derivative into the integral, which is afforded to us by the theorem that we just proved. Excuse me. And when you take derivatives, you get z to the 2n plus 1 minus 1, so you get 2n here. And then you get the 2n plus 1 cancels with the 2n plus 1, and you just get 2n factorial, and the minus 1 over n carries over. And this is valid in the entire complex plane. In some cases, we can find the Taylor or Maclaurin series via an identity. And if you recall, we defined the hyperbolic sine of z as minus I times the sine of iz, and we know what sine of z is, so we can take this Taylor series for sine, plug in iz, and then multiply by minus I, and that'll give us the Taylor series for the hyperbolic sine. So that's what I've done here. I have the minus I times sine iz, and I put iz in place for z. Then just expanding that out a bit, I've separated the I to the 2n plus 2. You notice because of the I here and the 2n plus 1 I here, so we get that. Then we get z to the 2n plus 1. And then the minus 1 here times the minus 1 to the n, it gives us a minus 1 to the n plus 1. And then we can simplify this expression and get this, which is not obvious that this equals 1, but I have it written out here. So just taking this part of the expression, then writing I to the 2n plus 2 is I squared times to the n plus 1. These two are the same. And then you get I to the minus 1 to the n plus 1, and then this is minus 1 to the n plus 1. And when you multiply that, you get minus 1 to the 2n plus 2, which equals 1. So we do get this expression here. Yeah, and we can do the same thing. Maybe it's an exercise if you're interested. try deriving the hyperbolic cosines Taylor series, or Maclaurin series, I guess, in this case, from the definition of hyperbolic cosine using the Maclaurin series for the cosine. Okay, I want to talk now about Laurent series. And basically, a Laurent series is a way of defining a series expansion for a function that has singularities or areas where the function is not analytic. And I've drawn a sort of the general situation on the right here. So you have an annulus, this gray area, where the function is analytic, and then there's a hole in it where the function is not analytic. And we can define a series for the given function in this gray area, and it's given by this theorem here. If a function f is analytic in an annular region, this gray area here, and gamma is a positively oriented simple closed curve, so I just gave you an example of that in here, within the annulus, then f has a unique series representation of the following form. So f of z equals the sum, notice it goes from minus infinity to plus infinity, c sub n, z minus z sub 0 to the n. So this is the Laurent series about z sub 0 of f of z. And then your c sub n is actually a contour. It's found by taking this contour integral that I've drawn here. For proof of this, I would refer the reader to Brown and Churchill. They prove the theorem in section 61, and then I believe uniqueness is proven in a separate section 66. Now it turns out that you don't normally need to use this complicated formula to find the Laurent series. I'll show you in the next several examples how that happens. Now the sort of good news is that we don't normally use that rather complicated formula to find the Laurent series. We kind of have a number of tricks or other methodology for finding it, and keeping in mind that the theorem says that it is unique. So if we do find Laurent series through some other means than that formula, then we know it is the Laurent series because of the uniqueness aspect. So let's take an example. We have e to the 1 over z, and we'll look at that. And notice the z, when you have z equals 0, this blows up. So we have our annulus here is the modulus of z greater than 0 and less than infinity. So we just have that one sore point where we can't take a Taylor series. So we plug in 1 over z into the Taylor series for e to the z, and we get this expansion here. And so this is our Laurent series, and it's defined everywhere except at z equals 0. So we can do another example. This is even simpler. If we had the function f of z equals this cubic divided by z, of course it doesn't, the function is not defined at z, but if we divide by z, we get this expression, z squared plus 3z minus 2, 7 divided by z, and this is a Laurent series for this function, and it's defined for all points z other than 0. Yeah, and just what I just said pretty much in this sentence here, but maybe one additional point. This is known as a punctured disk, so we'll use that terminology occasionally in what follows. Okay, let's try another example to find a Laurent series. We have the function f of z equals 2z over z squared plus 1. Note that z squared plus 1 can be factored as z plus I times z minus I. So we can write our function here partial fractions. I didn't show the details, but if you add these together with the common denominator, then you're going to get z, the product on the denominator, and then you're going to get z plus I plus z minus I, and the plus and minus I cancel, and you get 2z. So you can see this is the same. And what we want to do is find the Laurent series about z equals I. And to do that, we'll kind of use a trick here. We'll make use of this first term, since that's already in the form z minus I, and then we'll express this second term as a Taylor series about z equals I. And that's what I'm noting here. And the disk of analyticity for this function here we're going to take is z minus I less than 2. So this is a disk centered at I of radius 2, and it just misses the singularity here at minus I. So you might want to just think about that for a second. So this disk misses the singularity in this term in the function, and we're going to find the Taylor series for this. So let me jump ahead a little bit and do the computation for the derivatives we need of g of z, which I've done here. The nth derivative of this function is pretty easy to get. You just keep getting a minus, alternating minus sign here, and you're generating an n factorial, and then the power in the bottom keeps getting bigger. So this is the nth derivative of g of z, and then the coefficient in the Taylor series is this term evaluated at the point we're interested in, I, divided by n factorial, and that gives us minus 1 to the n, 2i to the n plus 1. And so I just go back here, and 1 over z plus 1 equals, this is our Taylor series formula. We just computed an. So we plug that in here. We can factor out a 1 over 2i, which I did here. And then we get z minus I over 2i to the n power. So that's the Taylor series. And so we just put this together with 1 over z minus I, and then you get these terms here, which are all z, or in the form z minus I to some power. You can write it like this if you like. It's not critical, but I wrote it this way just to emphasize that this is just constants times complex numbers, I should say, times z minus I to the n. And so we basically have our Laurent series. It has one negative power term and then an infinite number of positive power terms. And again, this is Laurent series about z equals I. What I'll mention, if you're interested in doing an exercise, is to do the opposite and do a Laurent series about z equals minus I, in which case you would use this part of the function as is, and then you would generate or derive the Taylor series for this part about z equals minus I, and you would get a similar formula to what we have here. Now on the next slide, I want to just explain a little bit of this, going from this step to this step, since there's some calculations involved. There was a little bit of complication in the last step of the problem from the last slide, and it involved this term here. I left out the z minus I to the n in the powers of 2, and I just wanted to look at the powers of I and the minus 1 to the n. and show how we got to this minus I to the n plus 1, which is what we had in the very last step. So what I did here is I took the minus 1 to the n and I to the n, and I just wrote it as a single term to the n power. And then keeping in mind, if you multiply the bottom and the top by I, the bottom becomes minus 1, which cancels this 1 here. And you just get I to the n, and then you have a minus I times that, and you just multiply the I times the n, I to the n, and you get minus I to the n plus 1. So just clarifying what I did in the last step, which may have looked like a bit of magic without some further simplification. Yeah, and I mentioned this before. We could have done the previous problem and developed the Laurent series about minus I, and I'll leave that as an exercise. And you can also check your answer for this alternate problem using Wolfram Alpha. I put this line in a command line, Laurent series 2z over z squared plus 1 about z equals minus I, and it actually came up with an answer. So you might want to give that a try, and you may also want to actually try to do it manually first. Okay, let's do another example. Let's take the function f of z equals z plus 1 divided by z cubed times z squared plus 1, noting that it has three singularities here, minus I, 0, and I. And we're going to compute we could have picked any one of these three, but we're going to compute the Laurent series about z sub 0 equals 0 in the region modulus of z less than 1 greater than 0. So punctured disk with 0 removed. We're going to use the geometric series formula, not just in this example, but we'll use it quite a few times. So the trick here is we write 1 over 1 plus e squared is 1 over 1 minus a minus e squared, and that's the same as this Taylor series, this geometric series, excuse me. And the minus gives you this alternating term, and so this converges for minus z squared, and the minus, of course, just goes away when you're taking the modulus, but it's z squared less than 1, which is equivalent to the modulus of z less than 1. And then we multiply this by z plus 1. And so you're going to get z times each one of these terms, and then 1 times each one of these terms, and it basically gives you this alternating plus plus minus minus plus plus minus minus. Gives you that series. Then we just finish it by multiplying by 1 over z cubed, and we get this as our Laurent series for f of z in this punctured disk. On this slide we have an example of showing that the Laurent series depends on the region of interest. We're going to take this function here, f of z equals minus 1 over z cubed times z minus 1. And first we'll look at the region absolute value, or the modulus of z between 1 and 0, so a punctuated disk. And we can take our function, factor out a 1 over z cubed, and then take the minus 1 and put it in the denominator. We get 1 over 1 minus z. Then we factor out, then we make note that this series here converges when the modulus of z is less than 1, and it converges to this function here, this expression here. Let me get this out of the way. And then we just multiply the 1 over z times the series, and we get our Laurent series for the function in this punctured disk. Then the other region would be when the modulus of z is greater than 1, and bound at less than infinity. And we have the problem that this is no longer convergent when the modulus of z is greater than 1. But we make note here that if the modulus of z is greater than 1, then the modulus of 1 over z is less than 1. And so the geometric series 1 over 1 minus, or should I say the geometric series associated with this expression 1 over 1 minus 1 over z does converge. And so we can write our function here, factor out the minus 1 over z cubed, and then factor out a 1 over z, and that leaves 1 over 1 minus 1 over z, and then we can expand this using the geometric series expansion, and we get this here, and then we multiply by the minus 1 over z to the fourth, and we get this expression here. So you can see these are not the same. We get two different Laurent series depending on the region of interest. For our final example, we're going to look at this function here, f of z equals z over z squared minus 3z plus 2. We can divide it into partial fractions. We first factor the denominator and then write it as partial fractions. I left out the details on that. You can easily check, though, that when you subtract these two and get a common denominator, you come back to this. So we have two singularities, one at 1 and the other one at 2. And that leaves us with three domains to consider. When the modulus of z is less than 1, when the modulus of z is between 2 and 1, and when the modulus of z is greater than 2. And each domain will give us a different Laurent expansion. So let's start with the first one. When the modulus of z is less than 1, we know that the Maclaurin series for 1 over 1 minus z over 2 converges when the modulus of z over 2 is less than 1, and when the modulus of z is less than 2. And the Maclaurin series of 1 over 1 minus z converges when the modulus of z is less than 1. So the intersection of these two regions is the modulus of z less than 1. We can put that information to use here. We rewrite our partial fraction here. It's minus 1 over 1 minus z over 2. And then we pull in the minus 1 here, and we get 1 over 1 minus z. Then it's just a matter of using the geometric series. We get z over 2 to the n, summed from 0 to infinity, and there's a minus sign outside here. And then this is just the sum from n equals 0 to infinity of z to the n. We can put these two together, and we get 1 minus 1 over, well, this first one is actually the second one here. 1 minus 1 over 2 to the n times z to the n, and the sum of that from n equals 0 to infinity. So that is our Laurent expansion for the domain when the modulus of z is less than 1. Okay, now we take the same problem, but the region is different. Our modulus of z is between 1 and 2. And we have that the following Laurent series, which I'll show you down here. So this one, it converges when the modulus of 1 over z is less than 1. And then the second one converges when the modulus of z over 2 is less than 1. So collectively, these two conditions imply that the modulus of z is greater than 1, less than 2. You have convergence there. And this is just rewriting our partial fraction from the previous slide. Okay, so we take the minus 1 over z and we plug in, we multiply that times 1 over z plugged into the formula for a geometric series, and then we have minus, and we plug in z over 2 again for the formula for a geometric series. You can pull out the minus, multiply the 1 over z into this here, and you notice I changed the subscript here, or the index, starting from 1 as opposed to 0 when you pull in the z. So that's the second Laurent series. We have one more. That's when the modulus of z is greater than 2. We'll do that on the next slide. So in that case, when the modulus of z is greater than 2, we again rewrite the partial fractions. And you notice here this first one converges 1 over z is less than 1, or when z is greater than 1, which is what we want here. And then this second one converges when 2 over z is less than 1, but that's when z is greater than, the modulus of z is greater than 2. So this is modulus of z greater than 1, modulus of z greater than 2. The intersection of those is the modulus of z greater than 2. So we can do the same substitution here. We do 1 over z and use the formula for the geometric series. We get this term. And then minus 2 over z plugged into the formula for the geometric series here. We multiply the minus 1 over z, or just the 1 over z, excuse me, and we get 1 over z to the n plus 1. We multiply the 2 over z into the second one, and we get 2 to the n plus 1 over z to the n plus 1. And then we subtract this from this, so we get 2 to the n minus 1 over z to the n. And notice I got rid of the n plus 1 by just starting from n equals 1 rather than 0. I could have left it at 0, but I started it at 1. So this is our solution. So as we see, we get a different Laurent expansion for each one of the three regions. Now, of course, if we had 3 singularities, then things get even harder, right? You would have 4 different regions in that case, and you would have a different expansion in each case. But I didn't attempt to do that type of example. But as you can see, things can quickly get very complex when you have a lot of singularities. Okay, so that's the end of this lesson. We have a few more lessons to go. The next lesson's on classifying the different singularities, and we'll get to that in a minute.